Okay, recorded and rolling. Today's Tuesday, August 30th. So a few announcements here. I'm not going to be here tomorrow. What I'll do is I'm going to set you guys up with a couple of free response questions. Sorry, I'm not going to be here to guide you through the first couple of those we do, but I'll have you guys work with each other. There's going to be two FRQs, two free response questions. So just do best to answer the questions. And then on Thursday, I'll go over the AP answer you guys and have you guys score yourselves. If you do terribly, it's not going to hurt your class grade, but just we got participation thing, okay? But there you go. Get some AP practice tomorrow. I do have your guys' quiz written and printed out, so I will give that to you guys on Thursday. Let's do a take-home quiz. So I'll give it to you on Thursday, and then you'll have a few days to do it. Been doing that last few years. It has some advantages. So one thing is we get more time in class to do labs and that sort of thing. Okay. Oh, and you guys remember I'm picking up your guys' homework on Friday. These are the college physics questions, right? It's college physics questions. Okay. And then when you guys come back from Labor Day weekend, have the AP classroom completed so that we can go over that, right? Okay. So you guys good? Good so far? Right. No, there's this one activity that keep trying to make time for and keeps getting bumped. You guys see these rulers on your desk? See the rulers? Right. Hey, if you came out with a friend, and suppose your friend was just holding the ruler, and you had your fingers down here at the 0 centimeter mark, okay? And your friend dropped the ruler, and you caught it as fast as you could. You think there's going to be some delay between your friend dropping the ruler and you catching it? Okay. Yeah. Oh, there is some delay between what's happening in the real world and what's happening in your mind. I wonder what that delay is, right? Suppose you're driving a car, something happens, you see something in the road in front of you, right? Move your foot over from the gas to the brake. Right? There's some human delay between human reaction time. And do you think you could use this setup right here to figure out exactly what that is? So underneath the screen card, I got an equation set up to start to handle that. I rushed through this at the very tail end of Friday. I know that was a few days back. So I think you guys can figure out what reaction time is based on the drop height. Here, I will give you guys this hint. Guys, as the ruler is falling, is it falling faster and faster and faster? Ooh, what's that called? Acceleration, right? Go ahead and take a minute with your classmates and see if you can figure out what your reaction time is. Right. Actually, while you guys are doing that, I'm going to go ahead and pause this video recording. So go ahead. All right, recording is resumed. Right, so this is a couple minutes into the future. If you're watching this video. All right, so to get this here, what I'm covering up with the screen card is, you guys remember those 3 kinematic formulas? And here, talking about these right here. They're on a green poster on my wall over there above that door. Okay. So if you pick the top one, that tells the top one is the only one that tells you the relationship between how far and how much time. Let's see, you're trying to get something about reaction time, trying to calculate reaction time based on the falling distance of the ruler. You guys see that the first equation is the only one that will handle that, right? The ruler falls in distance, you can accurately get that. Right? See, of all the tools that you use to measure in your labs, the one that's like the fuzziest that probably has the biggest error associated with it is using the stopwatch. And you definitely can't use the stopwatch to figure out the answer to the question, what's your reaction time? Because that's like trying to measure what is the very error of the thing. You know, you can't use the tool that has like that inbuilt error. But you can very accurately get this with the ruler. How far is the ruler fallen, and how long has it been falling for? Okay. Now we're going to use a simplified version of this because, guys, if you drop the ruler, let's say if you release it from rest, what is the initial velocity? 0. So doesn't this bit just go away? And it just boils down very simply to this. Okay. Instead of x, I'll call it h, like a height change. Be ready to feel that, right? Because displacement, there are a lot of characteristics for displacement. X is a really general one. H could be a height change. Okay. You guys see this could be this, right? Hey, can you guys solve for t based on the drop height? Let's solve it in terms of variables. Give you guys a head start here. See if you guys can solve for t in terms of all the other variables before I do. Okay. Can you get a general expression for t? So you just like pop in some height change and then, okay, that had to be the time. Let's see, I'm going to multiply the 2 divided by g. So 2 times the drop height, or however far it fell, divided by g. That's equal to t squared. Oh, and then I'm 1 algebra step away. What's the last algebra step? Square root. Yeah, square root. Great, and that'd be 2h/g. Okay, so you see, guys, how now we have a general expression. Okay, so you can take anybody's fall time, right? We got what 30 something students in here, so like 15, 16 pairs of students. Okay, you could plug in anybody's drop height for the ruler. Like suppose it was here, and then figure out what the reaction time was. Let's come up with an example. Suppose that this ruler had dropped, and so your partner drops the ruler and you catch it, shoot, and let's say it's at the 17 centimeter mark, 17 centimeters. Okay, somebody calculate what would the reaction time be for 17 centimeters? 17 centimeters. You guys know what G is, right? Yeah, you can use either 9.8 or 10 meters per second squared, either one of those, okay? Right? Yeah, what'd you get? Oh, okay, good.
Would it be 1.84?
Okay, I'm hearing 1.84, what? 1.4? Hang on, guys, if someone's been falling for 17 centimeters, 1.84, that's almost 2 seconds. Does that sound accurate? About 2 second drop time? Okay, like
0.184.
0.184? Ooh, does that sound a lot more reasonable? Like a fraction of a second? 0.184, that's about a fifth of a second. So somewhere there. That sounds a lot more reasonable. Right. Now, Elijah, what'd you do that you think maybe your classmates may miss?
The equations we use are in terms of meters. So 17 centimeters is 0.17 meters.
0.17 meters. Yeah, guys, remember to have all your units consistent with each other, right? So if you did here, if I said 17 centimeters, if you take this expression, time equals square root 2h on g. Okay, and in the calculator, if you plugged in 2 times 17 divided by, I'll go ahead and use 9.8 today, just because it's a little bit more precise than what we normally do. Okay, right. Then yeah, you would got square root 2 by 17 on 9.8. You said, oh yeah, like 1.8, 1.9 seconds. That's almost 2 seconds. Okay. Which, if you stop think about that for a moment, I don't really think that. What that means is here's 1 meter. You guys remember a meter stick? 1 meter. I'm trying to get this in the video too. Okay. How many of these do you, in this time interval, about 1.8, 1.9 seconds, how many of these would fall through your hands? 17, because the 17 represents 17 meters. Okay? But Elijah's on something. He said, 17 centimeters is actually what number goes here? 0.17. 0.17. It's 0.17 meters, and this is meters per second squared, right? So you can't mix and match centimeters and meters, right? Okay. So if I scroll up, scroll over, and just throw in a decimal right there, just a second inserted decimal. Now that looks like 0.186 seconds, around that's about 0.19 seconds, okay, which looks a lot more reasonable. In fact, that right there actually is pretty close to average human reaction time. Average human reaction time is about a fifth of a second. So there you go. So you probably catch it pretty close to that mark, close to 5 with a few centimeters. Okay. You guys good there? Good. All right. Yeah, so there you go. Now you guys can take that home, try that on your friends and siblings, figure out what their reaction time is. All right, next thing lined up. Let's do some more college physics questions. College physics. All right, so we did some of these yesterday. Continue this adventure. I'm going to skip all the way to the very last one. I think this one's pretty straightforward. It's the one that says in Bosnia. Kind of random side note here. I do remember this question back when I was in high school. So I'm wondering, had it became textbook in high school? I don't know. Could have. In Bosnia, the ultimate test of a young man's courage is to be able to jump off a 400-year-old bridge, and then the historical details. Yeah, into the river Neretva, 23 meters below the bridge. How long did the jump last? How fast was the jumper traveling upon impact with the river? And then, so we'll do this one at a time. There's a few questions here. Okay. The last detail here says if the speed of sound is 340 meters per second. Now that depends on pressure and temperature, but that's a pretty nice round value to use. How long after the jumper took off did a spectator on the bridge hear the splash? Ooh. So take some time to fall and then take some time for the sound to return back to the bridge, right? So, right. Okay, but we'll do one at a time here. So 72. We got bridge, river. Guy got to jump off. His friend is going to hear the splash after he splashes down. We got some sharks down here. Okay. And hey, you know what might be exciting is to solve this in terms of variables. Because if you solve this in terms of variables, then you could go back and change the bridge height and change the well, actually that's kind of the only number. Well, that's the speed of sound. Okay. Maybe we'll solve this all based on H and some general G. Right. So hey, you could even like hot planets and say what would the answer be on different planets, something like that, right? Okay. Right, so first question, how long did the jump last? Oh, is that what we just did with the reaction time with the ruler? Right? Because the ruler fell some distance and you had to back calculate what was your reaction time. Isn't this like the identical question? Right? So let's get straight to this. H equals 1/2 gt squared, which you can say because like if you start from rest, that whole v naught t part just goes away. Right? Okay. And the question is, how much time was the fall, right? So if you jump off the bridge, like, how long do you experience that fall? Can you guys solve for that? We just did that a couple months ago. Times 2 divided by g square root. Isn't that the answer right there? Right. This looks a lot like that, doesn't it? Now they said a 23-meter tall bridge. So let's see, let's do square root of 2 by 23 divided by, well, maybe 10, I don't know, 9.8 or 10, either one. Okay. Oh yeah, go ahead. Right. I'm getting like over 2 seconds. Right. Yeah, you guys are all getting a little over 2 seconds, right? 2.7 seconds. Yeah. Okay. Yeah. Okay. So that's what you should get, like 2.7 seconds. Okay. Here. This is if you're not getting that, I'm doing 2 times 23 meters divided by say 10 meters per second squared. If you use 9.8, that's perfectly fine too. Okay. But that's giving me 2.14 seconds. Okay. Okay, that's right. The follow-up question, well, actually, it was 3 questions. So, question B: how fast was the jumper traveling upon impact with the river? How fast? How fast? Give you guys a head start here. See if you guys can beat me to the answer. Well, here's one way to do it, not the only way. The speed you build up to just gt. Right. Gravity field is a type of acceleration. The full equation is v naught plus at, but start from rest, the v naught just goes away, right? Okay. Oh, and hey, time. Do I have an expression for time? Square 2h on g. Wouldn't that be like that? Okay. So the final velocity that you build up to is going to be g times the square root of 2h on g. Oh, look at this. G. Can I sort of partially cancel those out? Okay. Do a little algebra step here. You may or may not need this algebra step, but is this the same thing as the square root of g squared? Like that? G is the same thing as square root of g squared, right? Okay. Now, maybe your math teacher might say, well, it makes it positive or opposite value or something. Yeah, you gotta do it. So one of these going to cancel? It's going to be square root 2gh. Does that possibly look familiar? I'm pretty sure you guys seen that before. This pops up all over the place in physics. Okay. Galileo throwing stuff off Leaning Tower. How fast it going? Square root 2gh. Okay. Notice that time is not actually in the answer at this point because it got substituted out. Okay. Hey, could you solve this a different way? Because look at the way I said it. I started with this, which is just a simplified version of this formula, right? V naught 0, just AT, and then G is A. I started from the second equation. Could you jump straight to the third one and just use that instead? Okay. VF squared equals V naught squared plus 2AX. Guys, if V naught is still 0, because you just like step off the bridge, isn't it just VF squared is 2AX? Okay, here, what does that look like? VF squared is 2AX. But instead of A and X, could I just call that G instead of A and H instead of X? Right? Gravity is a type of acceleration. Height is a type of displacement. So VF squared is 2GH. Now I'm one algebra step away, which is to do what to both sides? Square root. So the final velocity would be the square root of 2GH. Oh, look at that. It's the same thing. So you pass through the force, get the same thing. Okay. Now it's in terms of variables. Oh, what if you want to plug in numbers? VF equals. That was what, 23-meter tall bridge? Okay. Or if you wanted to, since you had here, let me go way back to the top of this page. Since you had a value for time, it was like 2 point something seconds. You could just multiply that by 10, right? Hey, what is 2.1 times 10? 21 meters per second. Oh, so we just did that mental math, right? I hope I get about 21 meters per second here. Yeah. All right. That's what you're getting to. All right. 2 by 10 by 23 square root of all that fun stuff. Ah, it is. It is. Physics works. Oh yeah. Go back to the moon. All right, you guys go there. And there was one last question. We got the spectator on a bridge, and watches his friend jump off to go swim with the sharks, and then his friend falls, and there's splash, and then there's some time for the sound to return, so this guy can hear the splash. So that whole trip, right? This guy falling, and then the return trip of the sound. Right? What's that total time delay? Yeah. Good to figure that out. Here, I'll go ahead and just walk you guys through this one. Now consider this though. When the sound is traveling, guys, does sound care about gravity? No. So is sound accelerating, or is sound going to be constant speed? Yeah, we're going to use constant speed, right? Right. So I'm thinking this. All right, we got the here. We got this partly solved from part A. Remember, part A is the falling time. That's like half the answer right there, isn't it? Right. So I'm gonna throw a subscript on this time. I'll call this the falling time, and it's square root of 2h on g. So t fall equals square root 2h on g. We did that from before, right? Okay. What about the return trip of sound? So I'm gonna hold on to that. Can I say that the displacement, which is like the height of the bridge, is equal to speed of sound times the time that the sound travels back? Is that true? Okay. Could you solve for that t based on these two variables? It's one algebra step. What did you do both sides? Divide by the speed of sound. Okay. So when the time for the sound be the height of the bridge is divided by the speed of sound? Another true? Okay. All right, so we've got two time expressions. The time that the guy was falling and the time it takes for the sound to return. Okay, you guys see this? Hey, what do you guys think that t total is? Do you think it's t fall plus t sound? Right, you just add them together. So it's like 2.1 something seconds to fall, and probably a tiny fraction of a second for the sound to return. Okay, so here is the answer in terms of variables. So the total time is, this is for part C. Actually, this whole thing's part C, right? Falling time, which was square root 2h on g, plus the return sound, which is h over v sound. There you go. There's a general expression for the answer. Okay. So now you could plug in any bridge height. You could even change the speed of sound if you wanted to, or change the gravity field. Suppose you went to a different planet has a different gravity pull, maybe has a different like thickness of the atmosphere, and so sound travels differently, right? You could solve like anything. Right? Let's plug in some numbers though.
Good morning, teachers and students. At this time, please hold all students in your classroom until you get an announcement to release. Again, please freeze and hold students in your classroom at this time. Thank you.
Nobody move muscle. Alright, this is. Okay, that's 2.14 seconds plus 0.068 seconds. There you go. Also, this does look. Do you guys see how the return trip sound is a really tiny time interval compared to the falling time? That makes sense, right? I mean, that seems to check out. It makes maybe we should say that common sense or something, right? That takes about 2 seconds to fall and a tiny fraction of a second for the sound of return. Okay. All right, you guys good on that one? Okay. So you guys have the answers in terms of variables. You guys have numerical answers. All right, we're pretty good there. Oh, let's do. You know, I was gonna pick some more off this page and solve them. Does anybody have any questions about ones that I assigned? But before I just get rolling on some other ones. Any questions about any ones that I assigned? Oh yeah, which one? Ah, okay. All right, instantaneous acceleration on number 2. Okay, so they gave you a velocity versus time graph. Let's check this out. Instantaneous acceleration at the 2-second interval, or sorry, at the 2-second mark. Well, here's the 2-second mark right here, right? Okay, what's the graph doing? Hey guys, what property of velocity versus time tells you acceleration? The slope, because isn't acceleration a rate change of velocity? Okay, so what is the slope of the line right down here? 0, because so the rate change of velocity is 0, therefore the acceleration is 0. Yeah, 0 acceleration. Okay. So somebody's going at constant velocity, it looks like in the negative direction. Okay. Okay. How about at the 10-second mark? Well, at the 10-second mark, can you just do rise over run of this line? Okay. Let's get a quick estimate. Looks like it changes by 8 meters per second. It takes about 4 seconds to do that. I'm gonna just eyeballing it, say that's 8 over 4. That's about 2 meters per second squared. You guys think? You guys think about 2 meters per second squared. Okay. And then at 18 seconds. Well, here's 18 seconds. What's the slope of the line right here? It'd be 0 again, right? Okay, so 0 acceleration at 18 seconds. Okay. And then, you know, while we're looking at this one, let's go back to part I. Find the average acceleration. Okay. Guys, we'll almost never talk about that in this class, but it's good to just like see it once. But okay, just acknowledge it. Average acceleration, isn't that like change of velocity divided by time interval? Right. In this class, we care about instantaneous values and but just to do it, let's see, from 0 to 5 seconds. So 0 to 5. Well, actually, that's still 0 acceleration, isn't it? 0 to 5, right? Because it is for that entire leg. Okay. From 5 to 15. Actually, that's not much different either. We got a change of 16, right? 8 minus 8, negative 8. Guys, what's 8 minus negative 8? 16. Right? And that happens all in an interval of what's 5 to 15 seconds? 10-second interval, right? 1.6, right? 16 meters per second divided by 10 seconds is 1.6 meters per second squared. Okay. And then 5 to okay, right. Yeah, it'd be 0 for this little segment right here, right? Okay. Is that right? All right. Let's check out. How about this pair of questions, number 59 and number 60? Now, these are the same question, but one they give you numbers and the others in terms of variables. We're gonna start with number 60 here. Student throws a set of keys vertically upward to his fraternity brother, who is in a window distance h above. The brother's outstretched hand reaches, catches the keys up. on their way up a time t later, with what initial velocity were the keys thrown, and what was the velocity of the keys just before they were caught. And you can figure this all out in terms of h, g, and t. And then the previous question, number 59, is the same question. They just give you some numbers. So check this out. 5960. I like to draw a picture that helps me anyway. It's a good advice. So draw this. So 59 and 60, I'll call it. Right. We got like ground. There's like it's like a window here, some height up. This guy is reaching out. This guy down here, throwing some keys up. Okay. Now there's actually, oh, whoop, sorry, let me zoom out so you guys can see what I'm doing. Okay. Something like this going on, right? Okay. Now there's actually two ways that this guy could catch the keys. There's two paths the keys could follow. One is that the keys might follow this path, straight to him. Okay. I think I actually say that in one of the versions of these questions, either 59 or 60, straight to him. But the keys might also possibly like overshoot him, right, and then just lob back down. He catches them like that. Because it's two possibilities, right? So, yeah, whenever I'm solving problems, I like to think like big picture like that, just in case I get a kind of plus or minus. You know, that might show up if there's like a quadratic formula possibly. Because what would be the physical interpretation of having two possible answers, right? Or should I even be looking for there could be two possible answers, right? Some version of that. Okay? So what did they give us? What were they giving us here? Okay, so they told you h, that's a given value. From here to here, call that h. So we list givens. We got h. Of course, we would know g, right? Or sometimes it's implied. Right, so we're probably under, because I know we got fraternities. And also t is a given value. Okay, so it looks like somebody brought a stopwatch. So we got those things right there. And what do we want to find? What were the initial keys? Velocities. Okay, so find. Okay, how fast did this guy throw the keys? Call it v naught, initial velocity down here. It'd be like v naught, the little vector down here. Okay, and also v sub f, like the final velocity. So as the keys are being caught. Now maybe the keys are still on the way up, or maybe they're coming back down. Ooh, that could be like a sign difference, right? Okay. So I guess just in general, let's do some v sub f. Maybe lob it in, like drop that way, but it could be either way, right? Okay. Also, I'm thinking, you know, as I'm about to set up some equations, or hopefully you guys are staying a step ahead of me. If you are, then I'll solve these. Okay. This guy is throwing opposite direction of gravity. So I know in the equations there's going to be a negative sign somewhere, because if you're throwing the keys upward, the gravity's pulling downward. That's a direction difference, right? Okay. What would be some good equations to start with? Let's see. We know height, gravity, and time. Those are like the given values, because I guess we timed this for some reason. We're trying to figure out the either or both, actually both of the velocities ultimately. Okay. What looks like a good entry point? Which equation? First, second, or third? You like the first one? First one? Yeah. Okay. So I'm seeing some agreement on the first one. I like that too. Right. Here's why. If you pick the second one, then the two things we're solving for, well, those would both be unknown. And the third equation, well, same problem. But if you do start with the first one, there's only one unknown. One equation, one unknown. That's solvable, right? Or you could do two equations, two unknowns, but that seems overly complicated, right? So yeah, this is probably not the only way, but probably the easiest way to start solving this. Right, so let's do that. Let's go. The general equation, or I should say formula, we're gonna make an equation with it. X equals v naught t plus 1/2 at squared. Okay. Now that's a very general. I just pull that straight off that page. But let's modify it for the scenario, because the x we're talking about, displacement, isn't that h? Okay. So I could call this h. Okay. Now if I do that, I've already established a direction. You guys see if we're going from ground level. Actually, I should like the height change of the keys. I just go from where I threw it. But you guys get the idea, right? Yeah, just from here. Okay. Okay. If you're going from ground level up to the window. if H is a positive value, doesn't that imply positive is upwards? Right? Okay. If I do that, I could call V naught also positive. So V naught is positive value, and we'd like to know what that is. Okay. But gravity's pulling which way? Down. Okay, so now there's two ways I could handle that. I could do plus 1/2 GT squared, where I know G is gonna come out to be a negative value. Or if that bothers me, which kind of does, if I want G to be a positive value, I can put the negative sign right here, right? Because it's like slowing down, right? So minus 1/2 GT squared. Okay, so now I know I've set it up in such a way that I'm defining up as positive, down as negative. But I can call G a positive value, and I've taken care of the negative sign already. Is that okay? Okay? Not the only way to set this up, just one thought process. That's the way I would do it. Okay, hey, but one equation, one unknown, this is solvable right here, isn't it? We can just go ahead and solve for V naught. Okay. So I see three terms, take this term, add it over. So V naught T equals H plus 1/2 GT squared. Okay. And then solve for V naught. Just divide both sides by T. H over T plus 1/2 GT. Okay. There you go. There's a general expression where you could have any window height. You could time it with a stopwatch, get any time. Okay. You could even hot planets if you wanted to. Okay. And then you have some general expression that could always give you the answer. What's I want to say about the? Oh, let's see if the units are consistent. Guys, what's the units per velocity? Meters per second, right? I see three. Do you guys see three terms? Point, three terms. Do they all have to be in the same units, meters per second? Yes, they do. Yeah, if you're ever adding, subtracting terms, they have to have the same units. H over T. Hey, that's meters per second. Okay, that's an easy check. How about this last one? See, meters per second squared multiplied by seconds. Is that still meters per second? Yeah, yeah. So we're good. Also, remember that detail I said VF might be going upwards or downwards. So it could be sorry, we've got quite that yet. No, or sorry, that's the next question. So we still got to figure out what's VF. Okay. Now we got two ways we could handle that. What do you guys think I'm going to do? Second equation or third equation? I do like the second one myself. And reason is that this third one, because there's a squared value, sometimes you lose negative information. So sometimes it gets a little sketchy. Yeah, so I do prefer the second one if I have a choice. Okay, so let's go do that. Let's go final velocity equals initial velocity plus AT. Okay, now it's a really general way. Just pull it straight off the page. Now let's modify that for this scenario. Okay. So call VF, so that's fine. V naught, which I'm going to substitute this whole expression for that. Okay. And now let me think what I'm doing with G. Right. So gravity is the acceleration. So I'm going to replace A with G. But also remember what I did before is I'm calling up positive, down is negative. So I went ahead and just built into my equation, said included the negative sign. Right. Should I do the same thing here? Should I say minus GT? Yeah, I should. Right. Here's a different perspective of why that's would also be consistent. If this guy throws the keys upward with like some fast speed upward, then by the time this guy catches the keys, if the keys are moving on the way up, they would have to be moving slower, right? Have to be moving slower. Okay. So you guys see how whatever the throwing upward velocity is, you're subtracting from that, so it would be slowing it down, right? And the other thing that could happen is that the keys might overshoot and come back down. Now they'd still be moving slower, but they would be moving in the negative direction, right? Say in the same direction as gravity. Do you guys see how if you plug in a very large time interval, that would correspond with the keys like overshooting and coming back down, like lobbing back down. If you plug in a very large time interval, you guys see how the final velocity is going to become negative? That's to say in the same direction as gravity field. You guys see that? Right. These are all things to think about, how the mechanics of these equations are working. Like, what are they actually telling you, right? How do you read the music of these equations? Right. And I'm spitting a ton of questions at you guys, but these are all things I would think about, like as I'm going through this process to check out. And if you ever see something fishy, like, wait a minute, that doesn't really align with anything that would make any sense, then double check your math and see if you there's some kind of math error there. sometimes it's a good way to spot errors, like, wait a minute, that didn't make sense. But so far, this does make sense, okay? Right, so let's do a substitution, because this right here, this V naught, can I replace this V naught with this whole expression? Right, in terms of H, G, and T? I can do that, right? So final velocity is, right, I'll put this in brackets just so it stands out as a substitution, H over T plus 1/2 GT. Okay, that's the substitution, and it's all minus GT. Okay, so this substituted root point right there. Sorry. Right. Oh, what's 1/2 GT minus GT?
Minus 1/2 GT.
Yeah, -1/2 GT. Okay. Kind of like if GT represents $1, you have half a dollar minus $1, you have -$0.5, right? That helps at all, maybe. I don't know. Okay. VF equals H over T minus 1/2 GT. There you go. Now we got a general expression. So you can plug in any window height, any time that the keys were in the air, any gravity field for that matter, and you can figure out how fast the keys were moving at the time that this guy caught them. Okay, good for that. Yeah, and do you guys see two? Here, if this guy catches the keys on the way up, maybe have a positive velocity. If it catches them on the way down, be like a negative velocity. So there's two possible answers, right? And hey, I bet if you put in a small time interval, you could get a positive velocity. If you plug in a large time interval, eventually this term dominates and switches over negative to get a negative value, right? Is that? Do you guys think you could? That answers the whole question, right? That's actually number 60. If you want the answer to number 59, they just gave you numbers. You just pop the numbers in, right? Okay. I've got my own extension question. Could you guys solve for the amount of time that it takes to get from here to here? Could you guys solve for time? Right. And how many answers are there going to be? Two, right? There might be a short time, so bam, right there. There might be a long time, it's like wob, right? Give you guys a head start. So let's start from this expression because yeah, let's say in terms of the throwing velocity. Okay, solve for t. I know they told you time was a given, but suppose it wasn't. Suppose the throwing speed was a given and you had to solve for time. You could just take this expression and rearrange it and solve for time. Go ahead and do that. I want you guys to beat me to the answer. How much time take the keys to reach the frat brother? All right, I think that is a sufficient head start. You guys are beating me to the answer. All right, so I'm getting some looks like that. You may have gone through the algebra slightly differently than I did, but you should get something that looks kind of like what I got. You guys getting that too? Right, so walking you guys through this. Right, so I just started from this expression and saying, suppose that V naught was known just like H and G would be, but you have to solve for T. Cross multiplied everything by T. That's how you go from here to here. Okay. Then I see when I'm solving for T, let's see, it's squared there, it's linear here, and there's also a constant term here. So this is going to be quadratic, so I put it in this quadratic form.
Good morning, teachers and students. Thank you so much for cooperating with our freeze at this time. You can move freely around the campus. Thank you so much.
No, stay in my classroom. Learn about quadratic equations. So quadratic equation, which is actually on the if the equation base gives you quadratic equation, doesn't it? I think it did. Maybe I'm wrong. Anyway, you guys probably have quadratic equation memorized. I'll tell you what, AP exam though, I've never seen them ask I don't think I've ever seen them ask a question where you have to know this, unless I'm forgetting one. Okay. Anyway, cleaned it up, a few steps, you get this. And then you guys remember you were saying there should be two possible times. These might be on the way up or on the way down. Okay, so there you go. There's your plus and minus. Get that from quadratic. All right. Well, got about a minute class left, so not much time for anything else. Unless somebody has a question. If you have any questions about anything, any of the problems I assigned, right, we'll answer something real fast. So like I said, we'll see you guys tomorrow. Have you guys work in teams to solve a couple of FRQs. We'll go over those answers on Thursday. Then ideally, I'd like to get you guys started on projectile motion this Friday. Yes, they'd definitely be good because some of those are on maybe classroom too. So, all right. Well, that is a wrap on today.